Hi everyone, my name is Hamza Imran and I'm a design engineer at Imamba Private Limited, Islamabad, Pakistan. Today I'm going to present one of my papers which I presented at ICICD conference, which is a conference of IEEE which was held in IBA Karachi. The title of my paper is HPC as a Service, a Night Model. So the basic idea of this paper is that we try to brought some concepts of cloud computing to the domain of high performance computing. Here you can see that this paper is available on IEEE Explore, and I will put the description. I would put the link of this paper inside the description. Let's get started. So this work was done under the supervision of Dr. Ataul Aziz Ikram at EPIC Lab Embedded System and Pervasive Computing Lab at National University of Computer and Emerging Sciences, which is commonly known as FAST, at Islamabad campus. It was done by me and my colleague Saad Wazeer. The domains like big data, machine learning, and deep learning and other scientific and engineering research requires a lot of computer source, which makes the domain of high performance computing an important one. But the problem is that the supercomputers are out of range from majority of the people, especially from the people living in third world countries. Nowadays, supercomputers are actually made up by the creation of clusters of computers. So what you do is you pile up different commodity hardware and tries to combine their computer source to come up with a more powerful computer source, which we say a commodity cluster or a supercomputer. So basically the term supercomputer is actually a relative term. My smartphone is like a supercomputer from 1990s, right? So it's a relative term, which means a very powerful computer. By powerful, I mean which has more compute power. Okay. The problem is, which we tried to solve, was that in order to make use of such cluster computers, you need to have knowledge of, first of all, Linux, and the second was networking. So when someone tries to enter in this domain, basically when someone needs a supercomputer, which is actually a clusters of computers, he or she first needs to learn these skills, and which actually reduces the focus of that person from the actual work he or she is interested in doing. We tries to resolve this problem, and the solution is pretty a naive one. That's why the word naive is a part of our paper title. Let me explain that in detail. So what were our criteria, our main targets when we started working on this paper, this project? First of all, the first thing was that the hardware should be a commodity one. Basically, theoretically, any sort of computer, which can be a single board computer or even a smartphone, should be capable of computing its computer source to the overall cluster. We actually implemented the prototype on very famously available single board computers, which are Raspberry Pis. The second thing was that we tried to hide all the complexity of cluster usage from the end user, so that he or she can work on the actual problem he or she is trying to solve, instead of spending time on learning skills like Linux and networking. The third thing was that such kind of a computer, such kind of a resource should be available from all over the world, so that people living in underdeveloped areas, underdeveloped countries should also have access of it. So we divided this problem into three ends. We named that the cluster formation, the UI formation, which is actually going to be the end part where the end user is going to communicate with, and creating a linkage or interface between them. So this diagram on the right side of the screen is actually depicting the overall picture. We have the computer source, which actually is a distributed parallel computer, a distributed resource which have some computer source in some part of the world, the second computer source in some part of the world, that is somehow communicating to each other and working together. And then there is an interface creating node that is linking this to a web UI, which is going to be used by the end user on theoretically any sort of a device that can be a smartphone, a tablet, or a PC, etc. So the target was to come up with a cheap solution And to come up with a solution which should be helpful for everyone, we started triggering out, and finding out the solutions which are open source. So we, as I already told you, we divided the problem into three ends. Here is the software part, the software stack which we use to deploy or make such a solution. On the back end, the cluster formation, we used Linux. So Linux is running on every node, every compute contributing node. Then there's Ampich running on that Linux distribution. Ampich is basically a free open source message passing interface implementation. Message passing interface is basically a standard which is used in the domain of supercomputing for doing distributed computing. So basically, my target is to make this presentation easier to understand for everyone. So that's why I'm going to explain each and everything in layman's language. So MPI basically, first of all, what is a distributed system? So a distributed system is such a system in which your task is being distributed into chunks, and those chunks are being executed by different computers in parallel so that the execution process reduces. This is, in layman's language, a distributed system. Ampich helps you do that. Basically, MPI helps you do that, and Ampich is its free open source C-based implementation. Then, on the front end, basically upon Ampich, we used MPI for PY. So MPI for PY is actually a Python binding for Ampich. Our target was basically, you know that Python is becoming famous in almost every domain in computing nowadays, and it is also becoming famous in the field of high performance computing as well. So our target was that the end user should be able to run the Python code on the cluster. So for that, enabling that, we used MPI for PY. For creating the interface, we use MySQL, Apache server was running there, PHP, and there's a library called PHP cyclib which help us implement SSH and SCP protocol, which I'm going to explain why there was a need on these in later slides. So basically, we build upon our solution upon the open source as well as the already existing standard protocols. For the front end, we use Bootstrap, and the reason of using Bootstrap was to make our UI adjustable for any kind of a handheld device as well as a system. So, how we created the cluster, how it works. So, what happens is, inside of a cluster is that, so let's come towards how such a system works, how such a distributed system works. I'm not talking about our solution right now, I'm just talking about how a typical distributed system making use of MPI works. So basically, in case of a cluster, you have a master slave topology. Okay, you have one master node. That is the node. By node I mean a computer, a system. That can be a single board computer, that can be a full-fledged laptop of any PC, or that can be a powerful server. Okay, it's going to be one machine. It's going to, and then we will have theoretically any number of slave nodes, slave computing devices, slave machines. This master node is going to take commands from you, and then it's going to distribute the commands to others. What happens is, at the time of execution of a program, you tell to the master node how many processes you want to create. Processes are basically the same copy of the code which is running multiple number of times. Okay. So I'm trying to keep everything into the slide about distributed computing. So what happens is, in the case of such kind of a scenario, that you tell the master node, I want to create these much number of copies of my code, and every copy of the code, which is actually basically the same code, gets a unique ID which we call rank. And in your code, what you do is you put if commands which tells the process or that copy of the code that this particular chunk is being done by you. It's going to be executed by you. Okay, and these processes are capable of communicating with each other, and this communication is done by sending messages to each other. That's why we get the name message passing interface. Okay, by the way, one thing I missed in the last slide, and that was that master sends the commands to these slave nodes via a protocol called SSH, Secure Shell, which is a very famous protocol for remote accessing of a system. And then it needs to have the same copy of the code copied to all the slave nodes as well. For that, it uses SCP protocol. SCP is called secure copy, which is built upon SSH. It's also a famous protocol. Okay, now coming towards how such kind of a process works, how a typical MPI process works. So as I told in the beginning, every process is going to get a rank, right? In the beginning, okay, so we have that master slave terminology, master slave methodology, or master slave style in processes as well. Okay, the process master is going to get the rank 0, and it's going to run on the master node. All of the slave processes which have the rank starting from 1 till onwards can run on any node. Okay, we need to keep that in mind. If it's a master process, then you need to put this in your code that it has to combine the results derived or computed by other processes and has to return the final solution to the user. Okay, if it's a slave process, then it has to send its final results to the master process. Okay, moving towards our solution. So in our solution, there's a web UI in which a user is going to log in. The login credentials will be given by the admin. He or she is going to upload his or her parallel code. Making use of MPI on the web browser is going to enter how many processes he or she wants to create and going to hit the execute button. That file of the copy is going to be sent to the interface node, and that interface node is going to send to the master node, and it's going to SSH into the master node and going to tell it to execute that copy of the code n number of times which you have entered. The master is going to distribute it. All the slave nodes are going to contribute, return their results to the master node. Master is going to combine it and give the result back to the interface node. Interface is going to send that result back to the web UI running system, and the final output is going to be shown back to the user inside the browser. So we hide every complexity of sending a file, executing a file on server, using command line, etc. through this. Here you can see that someone uploaded the code of Monte Carlo simulation for finding the value of pi and enter the certain number of processes he or she wants to create, and here he got the output. Moreover, a system is going to maintain the files of individual user inside the database. Okay, there's a database that is maintaining users credential details, etc., and as well as the previous results, etc. Okay, so there are different modules of this web UI part. There are few things that are only visible to the admin, that is if, okay, by the way, as I mentioned in the beginning, you can add any number of clusters inside, any number of nodes, slave nodes inside your cluster. That part can also be done using basically the web UI. Okay, basically traditionally it requires a lot of manual processes. That is also made easier. You can find the details inside the paper. Okay, so here is the typical flow which I told you, which we created. So send program to the master node, right, via SCP protocol, then send commands to the master node to transfer the source code to all the slaves via SSH, and then send a command to the master node using SSH to execute and then read the output from the shell, display that in the browser, and then ends. This is the basic flow of our overall solution. Okay, coming towards the prototype, we actually had made a claim that our solution should be capable of running on any sort of hardware. So we had to make a prototype. We built that prototype upon single board computers and built that upon Raspberry Pis. So here is the cluster, here is the web server and interface node, and they are connected in through a network. By the way, this can be distributed. This thing can be in one part of the earth, and this can be another part of the earth, and the end user can be accessing it through another part of the earth, right? So your solution can be distributed throughout the planet, right? But so we created a cluster having 8 nodes, right? 8 Raspberry Pis and 3 Bs, and the interface node was 3B plus. We tested it using different embarrassingly parallel problems. Here is the algorithm for Monte Carlo simulation. Here is the results of running this on creating different number of processes. You can see that the execution time is being decreased, right? And the overall pattern should be like this if the system is not adding any overhead, right? There will be an overhead of transferring the files to all the nodes, and that would be in the beginning, just in the first time. Then things are going to be smooth. Okay. We like to thank Ignite for funding our project. They funded us under their Nigeria program. Thank you very much.